Hello, YouTube audience. This is my conclusion of my response to Professor Alexander Zenkin, a Russian mathematician who takes Cantor to task. This is also an apology for parts 1 and 2, for the light quality just was not very good. I'm responding to this particular treatise of his, Logic of Actual Infinity and G. Cantor's Diagonal Proof of the Uncountability of the Continuum. A recap of my argument very quickly. I take issue with the whole idea of potential or actual infinity. I don't believe it applies in mathematics, potential and actual. That's in, I think, part 1. Also, a recap of what a hyperreal is. A hyperreal is when we essentially rearrange the orders of the digits, like if I were to have y1 is equal to point y12, y13, y14, y15, dot, 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 y11. That's not a series that terminates at a digit, because that wouldn't be a real number. But what it actually means is point y12, y13, y14, y15, dot, 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 plus point y11. I have my philosophical qualms with that, because you're treating the order, well, it is kind of cardinal and ordinal, but you're divorcing it from the actual reals in a way. But as long as you're consistent, and what of course that really means is y1 is equal to point y11, y2, y13, y14. It's just a way of rearranging the digits. If you're consistent in the rules of how you construct hyperreals, I believe it is useful for Cantor's argument. If you are not consistent with the rules of how you construct hyperreals, and you just construct each row with a different rule, then the problem is at the point of infinity you've lost information. And we don't know at that point whether because if you just have a random set of rules, whether you actually have an infinite number of numbers or a finite number of numbers with numbers repeated. So I'm going to establish that from the outset, that I believe that only hyperreals that are constructed consistently, like this. This is getting into Professor Zenkin's argument, with the first digit of our real number put at the very end, and then our second digit becoming our first column here, our third digit becoming our second column, our fourth digit becoming our fourth column, and then we assume an infinite number of y values. And so we launch into Professor Zenkin's argument. He says, okay, if we do it that way, and we do our diagonalization argument, starting at y12, going to y23, y34, y45, and we go ahead and add 1 to each digit, well, we have a new string of numbers where we've lost knowledge here. In other words, let's say we then have our new string of numbers, y12 plus 1, y23 plus 1, y34 plus 1, y45 plus 1. And then we were to arrange that in hyperreal form. At that point, well, we would have point y23 plus 1, point y3 plus 4 plus 1, y45 plus 1, dot, 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 and then y12 plus 1. Well, we wouldn't have an argument for uncountability anymore. Now, QED, Cantor's argument depends on the order of digits, therefore it's not true. Well, for one thing, I would say that Cantor's argument is more of a proof by contradiction than it is anything else. So if you can find a contradiction once, you don't have to keep finding it over and over again. You've proven it by contradiction. However, I promised you a diagonalization argument that works for hyperreals. And again, it has to assume consistent rules for hyperreals. And so that's what I'm going to show you as my conclusion, as a direct argument against what Professor Zenkin is saying. Okay, let's take our diagonal, point y12, y23, I'm sorry, point y12, 2, 3, 3, 4, 4, 5, 5, 6, yada, yada. And then we're going to move the digits over one. Instead of point y12, we're going to have point something in the first digit place, call it x, and then y12, 2, 3, 3, 4, 4, 5, dot, dot, dot. Now, we still haven't established something new. We have not established that point x, y12, 2, 3, 3, 4, 4, 5 could not be included in an infinite number of y's. Okay, so now we're going to convert it to the hyperreal form. And in other words, we start off with just a regular old string of digits, but we're going to follow our consistent set of rules for hyperreal. So we can convert this to the hyperreal form, and we have point y1, 2, 2, 3, 3, 4, 4, 5, dot, 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 with x at the very end. So our first digit goes at the very end, and then our second digit goes first, and so forth. Well, let's add 1 to each digit, and we have, voila, y1, 2, 2, 3, 3, 4, 4, 5, dot, 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 to x plus 1 in hyperreal form. So, sure enough, we have something that it would be different from the first place value in the first row, the second place value in the second row, the third place value in the third row, the fourth place value in the fourth row. We've preserved information by moving these over by one digit place because, you know, Hilbert's Hotel, it can fit, right? And then we now have a hyperreal number that will not fit with any of these other hyperreal numbers. It is excluded because it is different from the, well, really, y12 would be the second place, but by the rules that we've established, we've redefined y12 as the first place. We have a hyperreal number now that's different from the second place, the third place, the fourth place. So we now have a hyperreal number that is not included. And again, that parallels Cantor's argument precisely, where we've assumed that the total number, that the countability of the reals can be ordered in rows, and we've now shown that it cannot be. And of course, we can put that in a row again, and then go through the very same process, and, you know, the process repeats over and over again, just like with Cantor's argument. So if we have a consistent set of rules for hyperreals, where we know with that consistent set of rules that we'll have an infinite, you know, an all if not infinite number of rows, for a consistent way of constructing hyperreals, we can construct a diagonalization argument for each of those hyperreals. I would suggest to you that you would have to get creative in how you did it. If you had, let's say, 2 numbers at the end, then you would have to maybe have 2 decimal places. The bottom line, though, is that it reestablishes the uncountability of the reals. Because if I have, put it up here again, all the reals, including transcendental numbers, arranged in this particular form, it's going to show the very same thing that Cantor showed. So that's my direct refutation of Professor Zenkin's claim of that Cantor's diagonalization argument depends on the order of the digits. It only does if the order of the digits is, well, it does not if the order of the digits is consistent. If they're inconsistent in how you construct hyperreals, then you can't necessarily make an assumption of infinity. Thank you.